Good morning, and welcome to Cambodia. It is now 6 a.m. and the action has started outside. I'm not sure what's going on, but something's going on. There's usually something going on, and it usually starts around 4. As I mentioned, I was going to wanted to do something. I will sleep in the meantime. I didn't want to look at that. I just want to find some documents from there. In my U-test program here, I've been fiddling around and making some threads. If you will recall, I have a class that simplifies the making and running of threads called TS thread, and like the dialogue class or window class or whatever, it has an associated proc type entry point, a procedure that you have to implement. In the case of a thread, the procedure is only ever called once, and when the procedure quits, the thread quits automatically. Just like a program. It is a program. The only thing about thread proc here is that you must call this function before proceeding. And all that does is let the person who initiated the running of this thread know that the thread is now running. And that part is hidden, so it has to be told. I have to tell you that. This here start function waits for this signal. So this would just sit here and hang forever if this is never called. I should probably change that in some way. Make it more obvious. Anyway, it's not that much to remember, and you only ever use things either you're using them all the time, in which case you know, or you hardly ever use it, and you'll figure it out eventually. The way, of course, to use it is to make up a class of your own, derived from the thread class, and implement a function. And what I wanted to show was that the FS segment is something that is thread specific. Each thread gets a different FS segment. And that segment has to be in a there must be a descriptor table, a local descriptor table, at least one wherein that segment is selected from. That is, the descriptor for that segment has to be in a local descriptor table, and that is proved by running this experiment. Now, I added a bunch of extra things here because there's more information in FS than just on fact. But let me just, without going through the details, run the program. Right here. Okay. Now, the function that made that printout is this here reg report. Initially, it was just printing out registers, but I added more stuff later. I added, for instance, a tag name to pass in so that we know which one we're talking about in the printout. A thread ID that the caller passes in, retrieved from whatever means they would normally retrieve a thread ID from, and a process ID in a similar way. For main, I'm passing in the word main. This function, operating system function, which is declared in winbase.h, get current thread ID, and get current process ID, also in winbase. Okay, so these are two operating system function calls, and just a name. Now, to actually have a look at the values of the segments, you do it like this. Thankfully, from these, well, I don't know if this worked in the 386, but it certainly works in the Pentium. You can move directly from CS into AX now. Remember, in DOS, you couldn't do that. It was always a problem. Oh, AXCS. How were we able to do that? Well, that's odd. I remember not being able to do that. It works? Why was I pushing and popping those things all the time? Maybe I just misremembered and I never even bothered to check. Okay, never mind. But I don't know if this will work. Maybe this will work too. It should. I got it on 1200 for the data rate, so it should be able to compile with the recorder on. Although it seems to. I might go back to the 1000 because it's okay. The picture's a little grainier, but I'm not. If I can compile. Okay, so it seems to work. So hang on. What I'm going to do is I'm going to cut this off here, change the settings back, and tack this on the head of the remainder. Because I'd rather be able to compile than have a pretty picture. Okay. Let's see now. You would have just watched that one. Okay, so you would understand that this here is making encoding the first bit that I just recorded. DS. No need for AX. SS. I don't know about encoder plus encoder, but I know that this was compiling. I was able to compile before. And you can see already faster, even with the extra work going on here. Now, that should give me the same printout. There it does. Okay. So from main, just look at the register bit first. CSDS SS FS is the familiar set. Now this is a different thread. Okay, you'll have to just take my word for it for now. It's a different thread. You'll note that these values are the same. The register values are the same. Okay? Now, this first one following the registers, is what appears at address FS selector FS segment :18, and this is supposed to be the linear address of the it's called the thread information block. Okay. A linear address would mean, in our flat memory model, the offset from 0 of the logical address of that data structure, and that turns out to be this. These 7FFD is the same for all of them, so a little space here, so you can see the difference easier. So for main, that's E00. For which one are we here? Thread 1, that's D000, and for thread 2, D000. I think I made a mistake in my printout. These are different for all three. Just make sure I didn't mess up. SEH. Frank ID 1, 2, 3, 4. Okay. Oh no, sorry. String 1, 2, 3, 4. 1, 2, 3, 4. Then 2. High low word. Oh, I know. Hang on a sec. I know I must have made a mistake when I was messing with this. Let me just find it. Oh, that's very odd. I didn't change anything, and now I see that these are different. Now I might have been reading it wrong. Now I have to stop this one and double check to see what I just saw, because I don't know. I can't go back and. Luckily, I caught it on camera. So I'm going to stop this one, add that to this list, and we'll try again. Well, we just got to the end. I might have to cut a few bits off of what I added. Yeah. So as you've just seen, for some reason, now we're into multi-threading. This is it could be a threading bug. They did print out the same values. The two threads printed out the same values for the one that I added, right? This one, FS18, which is that computed this way. So it would appear as though in thread 2 it was using the wrong FS, or the descriptor hadn't been loaded yet, or something. Or I doubt there was a task switch during the printf, because as far as I know, printf is can be considered an atomic operation. It might be that it had entered printf and it had worked out what it was going to print, and then a task switch occurs, right? And then we get the printout from the other. That could happen, but I think once it starts printing, it's called a lock. Let me just see if it does, how it does do that. This part I have the source code for. Printf. There's no worries about the first thread, but it'll use the same code. Now, yeah, here's the lock. Okay, so standard out gets locked before any decoding of the string or anything. So this printf contains that string identifying the thread, right? So whatever it says here, we can be sure belongs with this data, and we saw that this came out the same for two different thread identifiers. And they were different. The names here were different, I think. Let's check that again. Put it on mute. That says thread 1, that says thread 2. So, and clearly these are the same, which shouldn't be, as you saw. That should not have occurred. Now that's a real mystery, a really big mystery. There's no possibility that this could come out saying thread, oh, wait, no, that was passing on the stack. That one, I never, no, yeah, it was passing off the stack, but it was passed, the way it gets passed in is through the thread local storage, the operating system mechanism. So this says thread 2, because that was retrieved, that string was retrieved from thread local storage, and it's included with the rest of this printout, so therefore it has to be belonging with this thread. There was no possibility of a task switch between the prints, of a thread switch, sorry. and yet these two values came out the same. And TLS data has the same linear address, and yet it's reporting different values. It could be a bug in printout. You know, like something to do with the output function not flushing or something. But then you would expect to see only one printout, not three. Or it could be the kind of bug where the last, it goes E, D, what's the normal? The normal is still encoding. It goes down by one, right? So this one's E, D, E, so this one shouldn't be D, it should be C. It's like this one got printed out twice. So that's weird. Really weird, and it's a mystery, and you can be sure that it'll keep me up all night. All day, whatever. Okay. Well, this will now continue to the thing that's encoding currently. Okay, now apparently this works correct. This is showing the right result, or the expected result. This here address, the first one listed following registers, is supposed to be the linear address of the thread information block. It's called the thread information block. That address happens to be stored at FS18 hex, and it's different for each of these threads. Thread 1 and thread 2 and main all report a different result from that position. And the code to read that in is right here. Putting it into AX and then moving it into the variable. Right? Now, first, the segment selectors are all the same as before, okay? The fact that this selector is the same is the same in each thread, and data read at the same offset in each thread that's different, means that the selector value does not correspond to the same descriptor value. Now, I believe that follows from logic. A descriptor is used to translate selector offset values to logical address, or what they call linear address, and these linear addresses are supposed to be in line with the rest of the segments, right? Otherwise, it wouldn't be of any use. At least it should be in line with DS. So that means that the descriptor value is different. The descriptor for this that this selects is thread dependent, and so therefore the descriptor cannot be coming out of the same descriptor table because we're using the same selector, the value of that selector being 3B, and although it's not 100, I guess it's not 100% certain, because we still haven't figured out why that experiment with GS didn't work. Although the GS thing, I was never able to actually read anything, so I'm not sure what is going on with that. But it should be clear enough anyway that we're reading from it. We're giving the same selector. I'm convinced now that the interpretation of these selector numbers was, as the documentation told us, the format of the lower three bits are something to do with privilege, requested privilege level. Then the next bit is which table to choose from. Both of these indicate, according to the documentation, to use the local descriptor table, and both of these indicate using the global descriptor table. And and I believe that's probably what it's doing. So I think that just that bit proves, at least gives I'm giving it a 99% certainty that there is a local descriptor table, there's probably there can only be one, I think, probably per thread, one local descriptor table, and this happens to be entry, FS happens to be entry 3, which is the fourth entry in the local descriptor table. It points to a block. I don't know. The reason I had this open is because I had printed out what I retrieved from Wiki, the thread information block that points at the 0 at 0 is what they call a structured exception handling frame, which itself is a pointer. It's a linked list type thing, and so that's what happens to be a pointer at the beginning. The next thing says top of stack. Now I didn't print that out, but I am printing out the stack segment, and that comes from the global descriptor table. So we should expect that each of these threads, since they're given their own stack and not given their own stack segment, that would be possible because these are global, that the stack pointer ought to be different. So why don't we add that to this printout? Let's put it right after. It doesn't matter what I do it here. (175F). Oh, it's actually good that I split it up, isn't it? Well, no, it's totally different. 12FE6C. Now that looks like regular. Actually, what I should do for this one is just, you can still have things lined up if I do it like that. We have a little more flexibility. with this breaking it up. Come on. But you saw anyway that those ESPs were different, and they would have to be, because those stack segments are coming out of the global descriptor table. They can't point to different addresses, and so therefore the only way to make each thread have its own stack, and they are given their own stack, would be to have them occur at different places. If the stacks are given a size, there's a default size, which I don't know the value of it. I think it might be 1000 hex, but I'm not sure. I would try and get the help up. Too much going on. Come on, hang on. Okay, now it doesn't tell you what the default size is. It just says that either you can specify a value or 0, and if you specify a value, it could be incorrect. But if you put 0, you can't be incorrect, and the operating system, use the same value as the stack specified for the main thread. Sorry. I hope I don't still have this on 100 megs. It doesn't matter, actually. That number doesn't mean it's going to allocate that much memory. It's just that's just the maximum you could allocate. I'm curious to see what I've got it set at. Where is it? Here? Here. But set to the default. The amount of memory that's actually allocated for the stack is arbitrary. It could be any value. If you specify a certain reserve, then that alters where the stack is initially placed. We did that experiment, for instance, when I increased the stack size such that it couldn't fit below the executable image. The operating system decided, or whatever, the compiler decided to put it above. Right? It can choose the layout in any way it wants. You can change that layout, but whatever, doesn't matter. And so it put it 100 meg. It put the address 100 megs away from the executable image address. Now that's just a logical address, right? That doesn't actually even mean that in memory they're going to be separated by 100 megs. That would be impossible anyway, I think. Well, I don't know how many. I guess I have gigabytes worth of RAM. But even if it were more than the total, if that distance were more than the available RAM, it doesn't matter. The numbers themselves are logical addresses, and they don't necessarily have to be in one-to-one correspondence with physical address. In memory, however memory is for your program is split out. Suppose here's your memory. The memory arena, or whatever, logical. Now Now this you imagine for yourself as a contiguous block. Oops. Okay, and you use it as though it were a contiguous block. And now, at the end of the day, it has to eventually map to something, some kind of physical memory, right? Now, there's more than one type of physical memory. We'll call this RAM. Suppose this is RAM memory on your computer. And now there's an amount of space that's been allocated from your hard drive called virtual memory. Sorry, excuse me, sorry, excuse me. So this is memory that's allocated from the hard drive, usually quite a big number. I'm trying to indicate that here. I hope that I have sufficiently given you an idea of the relative difference. These things are, you know, in their orders of magnitude, how that might appear for a given process. Now, your logical memory space for your program might be on the order of, actually it's probably less than RAM memory. You usually have gigs of RAM, but your program usually only uses megs, right? This RAM is available for all processes. Now it's possible that your program, this address here, one chunk of it, let's say the X's, might be required to be used. That is, maybe you've got to run some code that appears in this logical address space. If paging is enabled, if we're using the paging mechanism, then this then all of this is broken up into 4 kilobyte pages, and the pages can be mapped into RAM or into the virtual memory on the disk. If we're going to use it, it has to go into RAM eventually. That's like global lock or something. You call global lock, and suddenly we find a free spot. Whoops. The operating system locates a place in memory to map this XX to, and then we can start using it. If this thing has been stagnant for long enough, the system recuperates this RAM, okay, and makes it usable for other processes. Well, and now it could be anywhere, doesn't matter, but it'll put put it somewhere on the disk in the virtual memory area. So either this memory, no, it doesn't have to line up, so shouldn't make it line up. This might be found somewhere in here, or it might be found somewhere in RAM. And this is the only thing that's not changing really is the logical view of it. In logical space, that memory is always at the same spot. In RAM or on the disk, that changes depending on what the system has available, you know, what they're selling today, right? So logical memory space is flat, contiguous, and unchanging. And these are just resources that your logical addresses map to, and they can be anywhere. Now, why was I talking about that? Oh, yes. So the stack, if I say I want to stack 100 megs away from my program, it will be 100 megs away in terms of logical address, but nothing will be allocated for that space. Only the numbers have been allocated in a sense. Nobody else is allowed to use that range. Okay, but that's just an agreement, right? Somebody could. But, anyway, now I wanted to run the program. So, here's the stack pointer for main, and that here is 179, and that's a digit more. That's 10 times more. These are above the program, and this is below the program, it turns out. So these threads, and the distance from here to here, the logical distance is 100,000 hex, close to 1 meg. And it's exactly that, right? The stack pointer, this stack pointer, which would be close, at the beginning of the program, it's near the top of the stack. That's the other thing just finished. One two FE6C. That's just over 1 meg, 1 million. Some of this is not used. I think there's a 1,000. The heap, the stack heap that's allocated starts at position 1,000 or 2,000 maybe from the base 0, from 0. Now these ones would also be close to their top, to their maximum, and this one, thread 1, there's some randomness. These might appear in a different order. 179 FE18, which is 24.7 million. Right? 24.8 million. And the other one is 89. And the difference is almost exactly 1 megabyte. In fact, that is 1 meg. The definition of a meg is 1,024 squared. Okay, it's exactly 1 meg. So they weren't very creative in deciding how to set these numbers. Okay, the default is 1. It says it took 1 meg. And actually, I already know, and maybe you know, I could have told you that without even looking at this, because we just read it in the help. They're given the same size as the same stack size as the calling process, right? And the default, I already told you, or I've mentioned 100 times, is 1 meg. That's all you get. which means that the end of the stack, this stack, well, I don't know where its starting point is. I'd have to look at the heap report, which I don't have. I don't think I might be printing it. And I turn that into a variable. What is that variable called? Doesn't matter, it's easy to find. And some of these are dead. This is the one we're using. U-test, right? Debug, U-test, oh, CRT debug. Dump model, yeah, I have that. Heaps, dump heaps. This I don't need, really. So here are the heaps. They should include oh, they might not include stack. They probably don't. I'll have to dump it again. I think I might dump it twice. Once at the beginning and once at the end, following my own advice. Do I? No. I should dump it again. Oh, wait. But there should be the, I don't need the second dump. I just need to find the first stack, which is here. Well, it's this many bytes, 12D00, and it starts at 20598. It's not exactly 1024, but it's close. There's some extra reserve space, I guess. This 588. What's this LP data? I wonder. Ah, yes. Okay. There's 588. Now there must be. This doesn't say 588. So there's another 10 bytes. There must be another 10. Just a buffer of 10, like a zone, like a separator of 10 bytes. Or they just add 10 on, I don't know. And then from 598 to here is the stack, the main program stack. So that all makes perfect sense. Everything makes perfect sense. Now the other things, what about these other things I was printing out? Um, Now, you'll notice that I'm passing in into this function, assuming I'm being honest to it, the thread ID and process ID as retrieved from the operating system. Now, it turns out that the process and thread ID can be retrieved from this thread information block structure. And the process ID should appear at offset 20. And that retrieves a C44 from main, and C44 from thread 1, and similarly from thread 2. And the operating system reports the same value. The thread ID is at offset 24. Operating system and main agree. C10, again, operating system agrees with the thread information block, and for thread 2, right? So you can retrieve these values directly from the thread information block. There's also another data structure I've told you about before, called thread local storage. Thread local storage. It happens to be that the thread local storage area is part of the thread information block, and it is located at offset 2C in the FS segment. And so that's where I get that value from. For the main thread, that address is FO2C. For thread 1, it's this value, and for thread 2, a different linear address. Right? So that's how thread local storage is implemented. So that's why that's what makes it possible for thread local storage, and I doubt it's a coincidence that they use the word local, because it's using a local descriptor table. That's how they implement it. Because this one of the segments is in the local descriptor table, they can reference this data, which is referenced through an index, right? The same index for all threads, and taken out of a special area called the thread local storage. In order to retrieve data, actually we should look at it, because I've put strings in there. Let's see. In the thread local storage, as I was demonstrating before, when I was first talking about threads, not for the main thread, so actually we've got to go one more. In thread 1, okay, I'm storing this name in the thread local storage because I wanted to demonstrate that you could put information in there and retrieve it with a global function, no this pointers or anything, that data. Now what do we got? Our thread information block, where is it? I've called it, okay, it's 77. I call it SEH. That happens to be the first entry. Whoops. 7FF DD or is it 000? Right? Now at offset, according to what I just said, TLS data, which may be a pointer already, but it's supposed to be at offset 2C. That's here, and that is obviously a pointer, right? I don't see the word thread, and that certainly looks like a pointer. 7FFDB2C. Now again, this looks like a pointer. Oh, that is a pointer because that's what I stored there in the thread information block. Somewhere I do that. I'm not sure if this is the one that I've stored, or I store a pointer to a structure. Here. You have to, no, it's I give its own file. Something like that. Oh, TLS man. Get TL. That just gets an index. But what do I store? A pointer to my data, which is a type this, which should have a bool, a D word, and a TS string. Well, that can't be a bool or D. Or could it be? No. Well, it could be. If it's packed. No, there's only two. Yeah, there could be a 0, possibly. If I read it backwards and it started with 0. But let's see. These look more like 2 addresses. 7FFDD2C. That's here. That's pointing to this address. And this next one, 7FFDE. 7FFDE000, which is nothing. I'm not sure. Oh, I forgot the 7. 7FF. This is not right anymore. I've got too many. Go back there. DDO2C. 7FFDDO2C. 7FFD. 7FFDE0. Now, that definitely looks, that's something mallet. But I don't see the string. Oh, the string though, if it were there, it would be a TS string. I don't see anything really. Oh, Wait a minute, it could start. It's a 0. Not sure. But anyway, you can see how this thing is. It's different, and that's enough to say that that's it. Oh, I'm on the wrong one. That's why. I go to the next one. Okay, this one, DC00. One. Oh, okay. Now this is looking good. 15C. That sounds like. I don't know what it sounds like. 15C FE7. Now, this again looks like a pointer. I don't know what this 88. 15C FEA4. FF34. This is a link. Oh, okay. Now how do I go back? This is a linked list. This is the regular heap, like the CRT heap. How do I get back? Where was that? 7FFDC00. Darn it. 7FF number 0. 15FE74. Darn it. Why didn't I think of that before? One five C FE74. Alright. Now, to make sense of this, this here looks like this is a stack pointer. And what this is, if this were my struct, I don't know what it might be, that was my struct. Bool, D-word, string. If it were packed, that could be a bool. D-word would have to be the thread ID. Thread ID is smaller number. Thread ID is D80. See that anywhere? I see a D80 here. Zero D80. No, it's not the same. An 80 and a 0D. But this thing here is definitely a pointer. I think this is the data part. stack pointer. Could that be possible? Five. I wish I knew it. I should. Anyway, sorry, I'm wasting your time. I'm sure that it wouldn't take long to sort out how this resolves into one of these structures. The implementation is quite, simple. Once you've got this structure, and you can put anything you want into it, and it's changed, and it's coming out of a local descriptor table, then you can have all this information. You have a nice place to store all this information. And what's kind of nice about it is the kind of information they chose to store in there. The one that we're interested in is this first bit, which we'll look at in the next video. This, I guess, is NT-specific, something to do with the NT subsystem. It looks like a lot of NT stuff here. Why do they say that? NT stuff. Let's see what that means. It could be that this part has to be of a certain format, and the rest you can do whatever you like with. This is from Wiki. There are two other pages I wanted to show you, but I don't have to use a lot of time. Way too much time. Sorry. I'll try and cut some of this out. Yeah. We'll get back to looking at these pages next time. There are four links that I'll provide. Not this time, because you got enough stuff to look at. But in the next video, I'll provide these 4 links. This here, this paper, written way back in 1995. Wow, I double-clicked. I used this. I remember reading this one. This particular article by Matt Pietrek has been and continues to be the reference for anything to do with structured exception handling. Everything just points to. Oh, there's a very good article you should read. It's about SEH, and here's the link. And it's always been this article. The same article, and it doesn't seem to have been modified. You can see how badly formatted it is and everything. But it's very helpful, and there's even example code in here. You can't tell immediately, but once you click on one of these figures, up comes this thing, okay, and all of the figures point to this same thing. So this is a great big block of code that you can examine and try running for yourself. And it explains the context structure and gives some usages. It uses inline assembler in his examples, and it's really quite a well written article. It doesn't go into too much. It goes into just as much depth as you need. Okay, I'll just have to stop here. See you.